Right, so our first main track speaker of this morning, we're going to introduce Hubert. So Hubert is an engineering manager at Snips, and look at this, production embedded. I'm so excited to find out what's going on here. So ladies and gentlemen, please put your hands together for Hubert de la Jonquie.
Thanks, Jonathan. So I would like to present to you today our current work on the embedded Rust at Snips. So first of all, I would like to explain a little bit what we are doing at Snips. Snips is a voice solution. So first, we take the main product of the company was with Snips Flow. It's a CPU voice platform where the goal is to let any client add a voice interface to any device. So how it works? You start with a wake word engine that will enable the system. Then you will have a speech recognition engine that will take the lead, and a natural language understanding that will try to map what the user is saying to an action that will need to be executed. Finally, we have a dialogue system to enrich the user interaction. All of this is running fully on device. So we have cloud performance, and everything is written in Rust. From this CPU product, we came 1 year ago to go to the MCU solution. As you can see, we can't do exactly the same thing because we have much more constrained environment. So we still have the wake word, and then we will trigger the automatic command recognizer and map it to a specific action on the device. Everything runs also on device. This ensures the privacy of the user, because what you say at home should stay at home. Oh, yeah. Yeah. So how it works? So as I say, you have a wake word, then a command to recognize. So your user will say, "Hey Snips, wash whites." What happens is that your washing machine will start a program to wash your clothes. You can do the same thing with the lights or other use cases. To enrich the user experience, what you can do is to enable a dialogue system. So for instance, you want to set up a whole program, you will start with a custom wash, then we will ask you which kind of wash you want to do, and then after a few rounds, we will set up the whole washing machine program. So what about Rust at Snips? Rust at Snips is the main language for every software we run on CPU and now also on MCU. We choose Rust because of cross-compilation, of course, performance and safety to go to production. We have few projects that you can take a look. We are fully written in Rust as Struct with a neuronal network inference engine. We have also Snips NLU with a natural language brick on our system with fully open source. And we have Rustling with a name entity system to recognize structured data inside queries that is available in different languages as English, French, Japanese, or Korean and Chinese. And German, sorry. So what are our constraints? So what we want to do is to go to the MCU world. So we target two main boards. So as you can see, it's cortex-m7. We usually came with 1 megabyte of RAM, and there is a lot of external flash. We have between 200 megahertz to 600 megahertz. It depends on what the client will pick up. But we also target the cortex-m4. So in which kind of environment we are running Snips? So the first thing to do in the system is to do the audio acquisition. And there is some transformation which is happening inside. It takes a lot of RAM because you need to buffer the audio. Then it goes to a second break, with the audio front-end. The audio front-end, the goal of it is really to clean the audio signal. Because the user can speak while playing some music, he can speak in noisy condition as a conference, or he can speak in the kitchen. There is many noise condition, and we need to have a clean signal. That's the goal of the audio front-end. The two first brick is not developed by us. So we don't know exactly how much processing time they will take, the RAM. We need to be comparable compared to them. Then we have Snips that will take the audio source and map to an action that the end client will execute on the device. Everything will usually use a real-time operating system because it starts to be a quite complex system inside the MCU. So, how do we do voice recognition? The voice recognition is split in 3 pieces. And there is different solution that can be done, but I will present one that we use at Snips. So the first thing you need to do is to extract key features on the sound. There is different way to do it. You have the MFCC features, the MEL features. I will go back to that later. Then you have a neural network who will try to take the features and output an intermediate decision that will be shaped by the postprocessor that will build the final detection that we want to recognize. So what about the feature extraction? So we extract the audio frame, and everything is based on the Fourier transform, because we map the audio to the frequency spectrum, and in a certain way that is near how we hear as human. Because we don't want to analyze sound that we can't hear because the voice belongs to a specific spectrum that we want to analyze. There is 2 options that is mainly used in this area, are the MEL feature and the MFCC features. How they work is that they take the energy on the frequency spectrum and apply filters and some matrix multiplication, and we get coefficient about what is happening. Then the neural network comes in action. So a neural network is a set of weights that usually are float points, and a set of operation to what to do with these weights. It's an active area of research because MCU are quite small, and running a float model is quite heavy because we are talking about around between 300,000 weights to 600,000 weights, or even 1 million. It's not because the model is big that it will be better, but at least we have to. Tiny model won't be efficient. So to do that, we apply a process that we call quantization. So each weight after the training, which is in floats, will be mapped to a 8-bit value. So your model size will be reduced by 4, and you can leverage that to use specific instruction on cortex-m7 to speed up the multiplication. There is mathematical operations that are provided by ARM in such cases. Then we have another particularity in our system, is that we analyze voice. The voice is a streaming input. And because of that, you can do a lot of computation caching that will reduce a lot the processing time. Because what we want to target is to have a read time factor less than 20%. So when the neural network is set up, we have different kind inside it of operator. So the classic one are the fully connected one. So we can see him as all the nodes are connected together. You have the convolution one is when you want to to mix over time the input. And you have so you have different subfamily as the dilated convolution and the depthwise convolution. They are designed to be more efficient with less weights. And then we have the LSTM with the long short-term memory for a different use case. All of that can run on MCU. When the neuronal network has finished, the post-processor will take the lead. Because the neuronal network can predict different things depending on what you want to do. There will be phones, words, and subwords. So the vocabulary, you can map it to a sequence of phones. And as you can map it directly to subwords, or it can be the final words you want to recognize. So the post-processor will try to map the neural network output to a recognition, to the vocabulary. So how to design such a solution, specifically for MCUs? We will split in 3 pieces the solution. We first do the model training in floats. You can use Python, TensorFlow, and all the frameworks who are already available in this area. Then we have built a model transpiler. So it will take a model from TensorFlow training, and then it will try to optimize it and output a minimized version of it for the MCU. And then we have the MCU library who takes the model and run it. So all the model transpiler is written in Rust because the company reads most of the software in Rust with standard library, so it's not embedded. And the MCU library, we started with a C code base because we started like more than 1 year ago. And now we are migrating pieces by pieces to Rust. So how the model transpiler will work? We take a feature extractor configuration, as I explained before, a neural network with train, and a post-processor configuration. Then what we do is that we reorganize the neural network in a way that we will optimize the operation with the weights. We also compute like a memory plan for allocation because the RAM usage is very critical. So by taking the advantage of the streaming property of the voice, we will change the architecture of the neural network to be so that we will really take this advantage without losing any performance in the final model. We also, one thing is that you will have part of the algorithm which depends only on the model, and other part will depend on the input of the user. What we try to do is that everything will depend only on the input will stay in RAM. Everything depending only on the model, we will pre-compute and try to have the best way to present it to the MCU to optimize the processing. Now we can, from the model transpiler, we can go to see what is inside the MCU, because we are here to talk more about MCUs. So the MCU library will take a serialized voice model, and then it will try to run it regarding the memory allocation plan that was computed by the model transpiler. We need, so to give like a lot of flexibility in the way that the algorithm works, what we try to do on the MCU library is to implement more and more algorithms that are available from research paper. It will give, for the machine learning team at Snips, a great flexibility to design the model, despite the fact we are running bigger and bigger models that are designed to do very more complex tasks. But at that time, the MCU code was in C. So now comes the interesting part, Rust on MCU. So we started to look at Rust 1.5 years, and because we need to go to the market, we choose to start with C. But a few months ago, we say, okay, now with all the new features of what was implemented for the embedded Rust, we take the decision to migrate all the code base to Rust. So why Rust? I think it's I don't need to say anything about Rust because everyone is convinced by it. But a few things that Rust have a package manager who is awesome and a cross-compilation features that make the development very easy. And also a wide ecosystem of crates that you can build on top of it that let you build new tools, new features, and new features, and also guarantee production quality. There is two things which is important in Rust is the memory safety and the ownership system, but also the zero-cost abstraction. What is very great with the zero-cost abstraction is that we can still keep the performance we had in C while have something we can maintain on the code base. But when you have the whole code base in C, and you are still trying to gain some processing time because your client, your partners want us to do more, and the whole ecosystem is in C, and you need to deliver a static library that do everything, but that will be called all the time by a C program. So from that, I will present you the first architecture of the system. So we have the application code who's written in C. Then we have different layers inside the library. The first one is a state machine that will, the idea is for modeling the user experience. So how to plug the wake word, the automatic command recognizer engine, and also the dialogue system to have full experience and to add a plug-and-play voice interface to your MCU. Then we need to coordinate all this algorithm. And then we have the critical part. Is where everything is critical in terms of RAM because it's where you will consume the most of processing time and the most of RAM. So the first thing we did is to reorganize the code base by following these different layers. Everything was compiled thanks to CMake, who was a great tool, but we wanted to do more thanks to Cargo. So what we did is that instead of rewriting everything, will take time, and we can't for that because we need to deliver every week to clients, partners. We take a different choice. We split the library in three. So we still have the bottom in C. Then we have the Rust part. We will take the lead on the non-critical part because it was the less risky for us to go still to deliver without any compromising on the performance. And what is very magic about Rust is that thanks to Cargo, we succeed to build a whole building system with only one line, one command line, Cargo build. So how to do that? You need to have something to plug the C part, the two blocks of C, and is where bindgen and C bindgen will come. And the build.rs is a key feature of Cargo that would enable everything to make it work. So you keep your CMake as you have before. Then, so Cargo, what we will do is that it will launch the CMake crate that launches the CMake system. You build your C code, then bindgen will take the next action. It will generate the Rust binding. Then you have your Rust code, normal code, of course with no standard library. And then when this one is compiled, we will launch the C bindgen crate that will generate the final C API for the client. So what did we win with that? First of all, Cargo becomes our new build system. So we can now build the whole library easily for a host computer, for the Cortex, and we can start to develop differently the solution. We have also the package management, which let us plug what we are doing with all the current Rust projects we have in the company. But well, the very good thing is that it brings a whole test system to our library. Because before it was very hard to test all the code and to have a good coverage. And with Cargo, it's like built-in to do integration tests, unit tests. Everything is there. And the final, as I said, is that you can start to take the whole ecosystem to build Rust application, but that will work on your computer. And sometimes, I will explain later, that you can do MCU development, but by writing on the host computer. Because what this brings, it's a new way to develop our system. Instead of developing everything for the MCU and deploy on the MCU, what we will do is that we will run only the audio acquisition, the audio front end to clean the signal, and then we output everything on your USB port, and the whole solution will run on the host computer. This will bring a lot of things, that we can start to build tools to analyze how our model behave in different conditions. So we can put MCU everywhere in the office. We collect the audio from different noisy conditions and see how our model will behave if, for instance, someone is saying, instead of a snips, something like a fish. It's very close, but it's not a snips. And one thing we notice, contrary to the CPU development flow, is that all the machine learning team was very far from the final product. And by doing so, they can install everything easily and run their model directly and understand what's happening. So it reduces the gap between the final product and the machine learning team. Now I will highlight some developments what we found out when we start to write Rust for embedded. So first, I will take a simple example, the Fibonacci. Well, it's not something new, but at least something. So the goal of this project is to show the 3 layers. So you have your C2 Rust, where you have a CMake configuration. And thanks to the build.rs, you will build this crate first. Then in the fib crates, you will be able to add features that you written in Rust. And finally, the one that will be built at the end for your client will be the FibRust2C. And this one we call the cBindGen. And by doing only a cargo build -- target with a cortex-m target, you will have everything that will be plugged. And is where the cargo magic happen. So we will take a Rust API we want to ship. So we have a computer, and the goal is to compute the Fibonacci sequence up to a max number, because after a certain value, it will take too much time. And then we will have an observer inside your algorithm. The goal of it is to know when you start the computation and when you end the computation. It will enable us to add a GPIO setup to measure the processing time that this function takes. Now came the C API. So what we want to do is that we want to develop the Rust as we want. And to do so, because everything is private, we will build like a raw block of memory. But because you have the build.rs, you can compute the size of your struct, your final struct, depending on your target, right away, and output an header file with the final number. And we will have two main functions: how to initialize the computer and how to compute the Fibonacci sequence. Compute the Fibonacci, the second method, it won't be a big deal in this kind of situation. But we will try to take a focus on how to initialize the computer, because C and Rust have different patterns for that. So this could be a first option. We have the classic new. We initialize the buffer with 0 values. And then we do an external C function that will take the C computer and just copy what is inside, to copy safely the computer inside the target pointer. Because in our case, we don't know where the client will put our memory. We don't do the allocation. They give us only the place to do the thing. But if you take the assembly code in release mode, you will see that Rust will place first. I don't know if there is a laser or no. Okay. So I will do it like this. So in this part, what happened is that this array will go inside the stack, then it will be copied inside the computer, then the computer will be copied inside the final pointer. But at the end, if you take the C API, your struct is already 4 kilobytes. But to do so, you will need 3 times more. So usually what we use is 40 kilobytes for all our system. We can't ask the client to have only to give us 120 kilobytes when in fact we are only using 40. So there will be another option. We'll do as C. We do an init function, but it's not Rust at all and not idiomatic. But so what we do is that we do as before. We take the raw memory, we initialize it. But this thing is dangerous because you break all the safety invariants of Rust. But at least in the assembly code, you don't see an overhead of the stack usage. But now you want also to build. So if you keep your init function pattern, you will say, okay, now I can build also the library for host computer. But because I'm on the host computer, I can use the standard library. So why not using the vector? If you do exactly the same initialization here, it will crash. The reason is quite simple. It's because as in C, the memory will be at 0 or something else. We don't know what will be the memory. But if you take the function before, what we do is that we do self.observer equal observer. And Rust, what it will do is that it will drop the previous version of the observer. But because it's something that is allocated on the heap, a free will appear, but you free something with not a pointer. So it will crash. So that was one of the first challenges we had to develop the library. Is because we wanted to have a lot of tools on the host computer that was using the standard library, but we want to run exactly what is inside the MCU. So this is a small highlight, but there will be in the coming months more highlight we can do about what we found in our development. Is that Rust and C behave differently, but they don't do the allocation in the same way. However, there is something we is called maybe an init. It's something that is still unstable, but it will be something. It can be one of our solutions to solve this problem, and we hope, and we know that it will be for soon. It will go to the stable, and it will let us mark for the compiler that it don't have to drop the vector when we will do the first initialization. So thanks for your attention. And if you want to learn more about Snips, you can go to our website, and you can build your own assistant on it if you want.
Okay, we've got a couple of minutes before our next speaker. Does anyone have any questions? Oh gosh, that was good, wasn't it? Production Rust this early in the morning. Okay, I saw a hand at the back first. Hang on a second. Do we have a second microphone anywhere?
Not unfortunately.
No.
So if the speaker could repeat the question.
Okay, we're going to repeat the question. Okay, so how much are we going to be seeing in open source, especially around TensorFlow?
Yeah. So as I said at the beginning of the presentation, we have already big projects who are open source, and it depends on what you want to do with TensorFlow specifically. But Tract can be a solution to run your models, and is fully written in Rust. So you don't need any more, because the issue with TensorFlow will be to do all the cross compilation, and we had to do that internally, and it was not an easy task, even if we open source like a binding for it. But it's very hard to every time, because we want to deploy our CPU solution on many hardwares. And every time we had to do specific adaptation for TensorFlow.
So would you replace it with again? Sorry.
Tract. So it's something we open source, and we have write a blog post 2 days ago. So it's very, and we work on it, and you will, so most of the solutions are designed for image classification and not for voice. And this one is really designed to take advantage of the streaming behavior of the voice. And you will observe like a lot of gain in processing time. Can be very fast. And it's based on the same system as us for the model Transpiler, but is embedded inside the library. So which feature I would like to be stabilized? But the first, so maybe an init, because this thing will help us to solve all the binding issue, and it's quite. We need to double check every time manually that we won't do, we won't crash. Unfortunately, it won't happen on the MCU, so it's the final one. But for all our host tools, it will be easier to not have to care about it, to leverage the Rust safety guarantee. So which RTOS we are using? So it's FreeRTOS. Sorry. But we are not dependent on any real-time operating system because we act as pure function to be sure that we can be integrated in bare metal environment as with RTOS. And it's not us who choose which operating system will be used. It's a final partner or client that will use for us. So we can't bring specifically an operating system to the market or push it. We can just advise that, for instance, in our case, the FreeRTOS is mainly used, or it can be RTOS, as in the next presentation.